So number of students are now decreasing day by day, isn't it? In the last class, I think total number of students were around 130 or so. Today it is around 90 or something, isn't it? Eventually it will be 10 or 20, is it? I mean, out of 220 students, it's unbelievable that 120 students, their internet is not working today at this time. Okay, let me just share the file. So in the last class, we started looking at the general concept of heat transfer, and then we barely started about the steady state conduction, isn't it? That is what we started looking at. So just to summarize the last class, we have discussed about the concept of conduction, convection, radiation. Then we have looked at steady state conduction in a one dimension. Then we started looking at Fourier's law of heat conduction, and we said that this is similar to Newton's law of viscosity. Then again we have discussed about the conductivity. We said that conductivity is a fundamental property similar to viscosity, and it depends on several things. It depends on the chemical constitution, characteristic of material, whether it is solid, liquid, gas, nature of the solid state, whether the solid is crystalline or amorphous, and the physical conditions like temperature and pressure, isn't it? Also, we have discussed about the thermal conductivity of metals, insulators, gases, liquid, etc. We said that the for a crystalline material, the conductivity is more than amorphous material because crystal structure helps in vibration, and that is why the conductivity of crystalline material is more. We said that again for metal, the thermal conductivity is primarily because of the movement of the electron. Uh, and thermal conductivity decreases with increase in temperature, similar to the electrical conductivity. Uh, Again, what we said is there are some substances which are having a low thermal conductivity called as insulators, and in such substances, in general, the from high wide volume is used because gases are poor conductor compared to the solids or liquid. Um, Again, in case of thermal insulators, if the temperature is increased, the thermal conductivity increases, unlike the metals. Okay. Uh, Thermal conductivity of liquid decreases with temperature, and thermal conductivity of gases increases with temperature. That is what we have seen. If you look at the order of magnitude of thermal conductivity of solid is around hundreds. Thermal conductivity of liquid is in if you look at the water, it is around 1, and for gases it is further 1 order magnitude lower. So typically for air, the thermal conductivity is 0.0262. In general, we take the thermal conductivity as constant average value, but it is a weak function of temperature, and it is given as K is given as K naught 1 plus AT plus BT square. Okay, but very often we use a constant value of thermal conductivity. Also, very often we take thermal conductivity as constant and not varying along the direction. But if it is varying along the direction, then the material is referred as anisotropic material. Okay. So this is what we started with. We started looking at the heat conduction through a composite wall consisting of 3 layers of material, 1, 2, 3. So again, these 3 layers are made up of different material having different conductivities K1, K2, K3. Their cross-sectional area is A. And in this case, we can say that the heat flown at a steady state will be same. So capital Q is going to be same through all three materials. Okay. So typically the Q is same, but if the area is not same, cross-sectional area is not same, in that case small q is going to vary. Small q is nothing but what? Heat flux, heat flow per unit area. So that may vary if the area is not same. So in this case, not only capital Q is same, but also small q is also same. Okay. So there is no heat generation, there is no area is also same. So in such cases, no shell balance is required, and we can directly get how much heat is transferred through slab 1, slab 2, slab 3 without any solving the differential equation. Okay, so no shell balance is required in this case. So we can obtain the heat transfer through the slab 1 directly as by applying the Fourier law of heat conduction. So we can directly get Q1 or Q as K1A. Change in the temperature in this first slab is going to be T dash minus T1. So sorry, T1 minus T dash divided by the length of the slab. So the length of the slab is L1. And if we rearrange this, we can find out temperature difference. So temperature difference is given as Q into L1 divided by K1A. And similarly, we can find out the temperature difference for layer 2 and layer 3. And if we rearrange everything, the overall temperature difference across all three slabs can be given as T1 minus T2 by summing all these temperature differences. So that comes out to be Q in the bracket L1 divided by K1A plus L2 divided by K2A plus L3 divided by K3A. Here L1 divided by K1A is the resistance corresponding to a thermal resistance corresponding to a layer 1. L2 divided by K2A is the thermal resistance corresponding to layer 2. And similarly L3 divided by K3A is the thermal resistance for layer 3. Okay, and if we sum all these thermal resistance, that gives the total resistance of across these three slabs. Isn't it? So in this case also you can see that the resistances are additive, similar to the electrical resistances, and that is why this electrical circuit diagram is given here, where all the resistances are given in series. So again we have seen the analogy between the current and the thermal heat transfer here. So both are nearly the same. The rate of heat transfer is again given as temperature driving force divided by thermal resistance, which is similar to how the current is defined. So current is given as potential difference by electrical resistance. Okay. Then we have looked at one problem, and this problem we have solved in the last class. So is it everything all right till this point? Is it clear, everyone? Can we move further?
Yes, sir.
Yes, sir.
Okay.
Sir, please explain the direction of the heat flux. What is written in the bracket? I didn't understand.
Just a minute. Okay. So what you are saying? Where is the confusion?
Sir, heat flux in the previous slide when heat flux is introduced.
Here?
No, previous, more previous slides.
Here?
Yes, sir. Yes, sir. Heat flux.
Okay.
Rate
So
of heat conduction normal.
So small qx is a heat flux, that is the heat transfer per unit area. So watt per unit per meter square, that is what the unit of this small qx is going to be. So this is nothing but the heat flux, rate of heat conduction per unit area normal to the x direction. Okay, where in this case x is the direction of the heat transfer. Is it clear or not clear? How it is related to capital Q? This small qx multiplied by area will give you a capital Q.
Okay, sir, got it.
Okay, so this equation is similar to what we see in a Newton's law of viscosity, isn't it? So Newton's law of viscosity, shear stress is given as minus mu into dV by dx, isn't it?
Yes, sir.
So this is similar to that. So in this case, the rate of heat flux is given as minus k dt by dx, where dt by dx is nothing but the temperature gradient along the x direction, and k is the thermal conductivity. Okay, but the integrated form of equation is given by this. So if you integrate the same equation, you are going to get this across the length, isn't it? So capital Q will be given as Ka delta T divided by L. Is it correct?
Yes, sir.
So in case of a slab, what I was saying is in case of this slab, we don't need to write a shell balance at all, because the cross sectional area is same. So that means we can directly write down in terms of Q. We don't need to write down the balance equation in terms of small q. Usually we write the balance equation in terms of small q whenever there is a change in the area, or whenever there is a generation of the heat, whenever there is an unsteady state, heat transfer is involved. All these complications we are going to look at one by one. So far we are only looking at a very simple system where area is also not varying, where there is no accumulation, there is no generation of the heat. Okay, so that is why we have not used a shell balance in this case. It is not required. Okay. All right. Okay, so let's move to the slightly complicated case now. So as I said that in the previous case, we have not used a shell balance at all, because the cross sectional area was same. Cross sectional area was same as A. But let's look at another example where there is a hot liquid is flowing through a pipe, and we are interested in finding out how the heat will be conducted through the radial direction. Okay, so this is the radial direction, how the heat will be dissipated to the outside ambience through a radial direction. That is what we are looking at. So now you can see that inside this pipe the radius is going to be Ri, but outside the radius is R naught. That means the area is continuously varying as you are moving along the radial direction. Can you see? Is it clear to everyone, the system, at least what I'm trying to say?
Yes, sir.
This is the pipe. In this
Yes.
pipe, the hot fluid is flowing. We are interested in finding out how the heat will be conducted out in a radial direction. And as we see in a radial direction, the cross-sectional area is going to vary. Inside this pipe, the cross-sectional area is going to be 2 pi RIL, whereas outside the cross-sectional area is going to be 2 pi R naught L. Okay, even though we are looking at the steady state system, that means there is no accumulation, there is no generation, but still in this case we need to make a shell balance. Okay, we need to make a shell balance, and such situations commonly occur in a process application. So flow through a pipe, or a flow across the spherical pellets. Isn't it? All such things you will see in a chemical engineering or process application, where the area of the cross section is going to vary as you move along the radial direction. So in such cases, if you wanted to find out the heat conducted through such systems, we need to make a shell balance. Is it clear to everyone? Hello?
Yes, sir.
So we are
Yes, sir.
slightly complicating our system. In the earlier case, we have used the area constant, but now we are slightly adding one difficulty. So we are only looking at now the variable area. Eventually, we will add even the generation, accumulation term, etc. As we move ahead. Okay. So as I said, in this case, we have to make a shell balance to find out how much heat will be conducted out through the radial surface. Okay, so let's assume a shell here as shown here. This is the shell at the radius r. The thickness of this shell is delta r, and this delta r is tends to 0, isn't it? That's what we do in a shell balance, correct? Inside temperature is Ti and outside temperature is T naught. Okay. So now in this shell, whatever the heat Q, capital Q input is there in this shell, the same will be the going out, isn't it? Because there is no accumulation, there is no accumulation in this shell. So that means whatever is the heat input to this shell, which is shown by this in between annular space, which I have shown by the cross lines here. Okay, so whatever the heat input to this shell is, the same is going to be output, because there is no generation, there is no accumulation. So we can write that the rate of heat input to the shell at the radial position R will be given by what? Area into flux, isn't it? So area in this case is going to be 2 pi RL, and the flux is going to be QR, small QR, and that we are calculating at the radius R. So that's why I have given this 2 pi RL QR at R. Similarly, the rate of heat output from the shell at a radial position R plus delta R. R plus delta R is the outside radius, isn't it? Outside radius of this shell. So what will be the rate of heat output? Rate of heat output will be 2 pi RL QR, again calculated at R plus delta R, isn't it? And what will be the balance equation in this case? At the steady state, there is no accumulation. Accumulation is 0. There is no generation term. That means rate of heat input will be same as rate of heat output. So this 2 pi RL QR at R is same as 2 pi RL QR at R plus delta R. Is it clear to everyone what we are writing here so far?
Yes, sir.
So similar things you might have done in your transport phenomena earlier, isn't it? So we can rearrange this equation. This equation, if I take this right hand side on the left hand side, what I can write down is 2 pi RL QR R plus delta R minus 2 pi RL QR at R equals to 0. And again, I can divide this entire equation by delta R. Doesn't matter, because right hand side will be 0, isn't it? So if I divide this equation, I get this equation like this. Okay. Now this is nothing but what? This is nothing but the definition of differential, isn't it? For delta R tends to 0, limit delta R tends to 0, this equation can be represented as d by dr of 2 pi RL QR equals to 0. Are you all agreeing with me? Isn't it? 2
Yes.
pi RL is the constant term that I can take it out. So what we are going to get, 2 pi L is a constant term that I can take it out. So what we will be left with is d by dr R QR. And that is equals to 0, because this R is varying. Remember here in this differential equation, R is varying. So R is not constant, but 2 pi L is constant, so that I can take it out, and right hand side is 0. So we can write down this as d by dr is d by dr of R QR equals to 0. Are you all agreeing with me with this?
Yes, sir.
Yes, sir.
Now this d by dr R QR equals to 0. So we can integrate this term. We can integrate this term. So after integration, what we are going to get is R QR is going to be a constant. Let's say C1, isn't it? That's what we are going to get it. R QR is a constant C1. Now in this case, what is QR? QR is nothing but a heat flux, and heat flux is given by a Fourier of heat conduction. So in this case, what will be this QR? In this case, the QR is going to be minus K dt by dr. Again, we are assuming that this thermal conductivity K is constant here, isn't it? So QR is given by minus K dt by dr. If I put QR equals to minus K dt by dr in this equation, what we are going to get is R in the bracket minus K dt by dr equals to C1. We can again rearrange this equation. What we get is dt by dr is given as minus C1 by K 1 by R. Isn't it? Just by rearranging. So this C1 by R we will have, and again we will divide this K minus K here. So we will get dt by dr as minus C1 by K 1 by R. And again we can differentiate, we can integrate this equation with respect to R. So after integrating this equation with respect to R, what we get is T is given as C1K ln R plus C2. Isn't it? So this C1K is a constant term. We can take it out. Integration of 1 by R is going to be ln R. This minus sign remain as it is, isn't it? And since we are integrating here, one more integration constant will be added. So plus C2. Is it clear to everyone? This part, what we are doing?
Yes, sir.
Yes, sir. Yes, sir.
So now this is what the integration equation we have obtained, which is describing the distribution of the temperature across the radial direction. But we need to find out constant C1 and C2. So how we can find out constant C1 and C2? We can find out this constant C1 and C2 by applying the boundary conditions. So what are the boundary condition in this case? Boundary condition is at R equals to Ri, my temperature is T1, Ti. And R equals to R naught, my temperature is T naught. These are the two boundary conditions. If I put two boundary conditions in this equation, I can get rid of this constant term C1 and C2. So these are the boundary conditions. At R equals to Ri, my temperature T is Ti. And at R equals to R naught, my temperature T is T naught. If I put the first boundary condition, what we get is Ti is given as minus C1k ln Ri plus C2. And similarly from the second equation, what we get is T naught is equals to minus C1 by k ln R naught plus C2. Okay, now we can subtract both these equations. We can eliminate this constant C1 C2. So what we get is Ti minus T naught, Ti minus T naught. If and then we can divide this. So what we will get is C1, isn't it? So C1 is obtained in this case is Ti minus T naught k ln R naught by Ri. This is just by subtracting this first equation by second equation and then rearranging. If I subtract this second equation from the first, then this C2 will get cancel out and we will have only constant C1 left. So C1 we can rearrange this equation and find out C1. So C1 comes out to be this Ti minus T naught into k divided by ln R naught by Ri. Is it clear how we have got C1 here?
Yes, sir.
Again.
Yes, sir.
Again here, if we can put this C1 in this original first equation, so we get Ti equals to minus C1 by k ln Ri plus C2. So this C1, if I replace by this obtained C1, in this case we can find out C2. So C2 comes out to be Ti plus Ti minus T naught ln Ri divided by ln R naught by Ri. Okay, and if you put this C1 and C2 again in the original equation 3, what we get is the temperature distribution, and the temperature distribution across the radial direction for a cylindrical geometry, that is given as T is given as Ti minus T naught divided by ln R naught by Ri ln R by Ri. So here by using this equation we can find out what will be the temperature T at any radius R. Okay. So this is what the temperature distribution is. Now we wanted to, our interest is to find out the rate of heat transfer Q. So I can go back. What is rate of heat transfer Q? Rate of heat transfer, remember as I said, my rate of heat transfer is same at any location. My capital Q is same. Whether I am calculating that capital Q here at this inner surface or outer surface, that Q is going to be same because there is no accumulation in this system. Only thing which is going to vary across the radial direction is small q, which is nothing but the flux. The flux is going to vary, but not capital Q. Capital Q is going to be same. If my capital Q here and the capital Q outside here is different, in that case, I will either have a accumulation term here, isn't it? But there is no accumulation. It's a steady state heat conduction. Steady state heat conduction. That means the Q here and the Q outside is same. So that means I can find out Q directly at any location, isn't it? Sorry. Can find out Q at any location. So remember QR I have obtained here, isn't it? So QR into area is going to give me capital Q, isn't it? But RQR is just C1. RQR is C1. And if I multiply this equation by 2 pi L, then it is going to be area into QR. Isn't it? That will be just capital Q. So if I multiply 2 pi L to this C1, that is going to give me capital Q. Do you all agree with me?
Yes, sir.
Isn't it? So if I multiply this C1 by 2 pi L, that will be what? 2 pi R L QR. That is nothing but area into QR, isn't it? So C1 into 2 pi L is nothing but capital Q. That is what we have calculated here. So rate of heat flow Q is area into heat flux at any radius R, because Q is not varying. Q is going to be same. Capital Q is going to be same. So that is given as 2 pi R L QR. That is nothing but 2 pi L C1. And C1 we have already calculated. C1 is this. C1 into 2 pi L, if I do, what we get is 2 pi Lk Ti minus T naught divided by Ln R naught by Ri. So this is what I am going to get the rate of heat flow across the cylindrical surface. Now in this case also, what is driving force? Driving force is Ti minus T naught. Isn't that the total temperature difference is a driving force? Thermal resistance in this case will be what? Ln R naught by Ri divided by 2 pi Lk. That is going to be thermal resistance. Now this entire equation, if I multiply and divide by R naught minus Ri, if I multiply this equation by R naught minus Ri and divide by R naught minus Ri, equation is same. We are only multiplying and dividing the same term, so it doesn't matter. So if I do that, I can represent this equation slightly in a different way. So see, this R naught minus Ri will be what? Thickness, isn't it? This is going to be a thickness. But ln R naught by Ri divided by R naught by Ri is going to be what? That is going to be 1 by Rm, where Rm is nothing but the log mean radius. So I can represent this equation as 2 pi Rm Lk Ti minus T naught R naught minus Ri. Now this equation is similar to the equation which we have seen for a flat geometry. It's the same equation like a flat geometry here, isn't it? Delta T divided by C. In this case also we are taking the thickness here at the bottom, isn't it? And K1A will be the area in the numerator. If I look at only one slab, for a one slab I will get Q as K1A delta T divided by L, L1 or L, isn't it? So that means what? This equation is also going to be the same. This R naught minus Ri is going to be thickness of the cylindrical area, isn't it? 2 pi RML, that is going to be what? Area. So AK delta T divided by thickness. So this equation is similar to the equation which we have seen for a flat slab. So what we can conclude here? We can conclude here is, if we calculate the area based on the log mean radius of the cylinder, in that case, the same equation as that of the slab can be used for calculating the heat transfer in a cylindrical case. Do you all agree? Hello?
Yes, sir.
Yes.
Yes, sir.
So this is also one of the, question people ask in the interviews. If I wanted to use the equation of the slab for a cylindrical case, what will be my radius? So radius is going to be log mean radius. Okay, in case of cylindrical. All right.
Yes, sir.
Okay. Next move to let's make our analysis little bit more complex here. Now let's look at, there are multiple cylindrical slabs are there, isn't it? So this analysis can be extended in a similar way, the way we have looked at the flat slab. So in this case also, let's say if we are having the multiple slabs one after another in a radial direction, cylindrical slabs one after another in a radial direction. So in this case we can write down the remember the capital Q is going to be same, isn't it? So capital Q for each of these slab is going to be what? For a first slab it is going to be 2 pi Lk1 Ti minus T dash divided by Ln R dash by Ri, isn't it? Ri is the inner radius and R dash will be the radius at the interface of slab 1 and slab 2, isn't it? Similarly, for a second slab, it will be 2 pi Lk2 T dash minus T double dash divided by Ln R double dash by R dash. And for this last slab, third slab, it is going to be 2 pi Lk3 T double dash minus T naught divided by Ln R naught divided by R double dash. So I am writing the same equation for individual slabs here, and I'm equating all these because the heat transfer through each of these slabs is going to be same. Does it make sense? This first equation to everyone?
Yes, sir.
Yes, sir.
Sir. Now, from these equations, I can still find out what will be the temperature difference across individual slab. So for a first slab, the temperature difference is going to be Ti minus T dash. For a second slab, it will be T dash minus T double dash. And for a third slab, it is going to be T double dash minus T naught. So I can individually find out that. So Ti minus T dash will be what? Q into ln R dash by Ri divided by 2 pi Lk1, isn't it? So in a similar manner, I can find out the temperature difference for all these individual slabs and I can add them. So if I add them, what I'm going to get? I'm going to get the overall temperature difference across all three slabs, and that is given as Ti minus T naught. So Ti minus T naught is given as Ti minus T dash plus T dash minus T double dash plus T double dash minus T naught, isn't it? And Ti minus T dash is given as Q into ln R dash by Ri divided by 2 pi Lk1. Similarly, T dash minus T double dash is given by the second term here, isn't it? So which is ln R double dash by R dash divided by 2 pi Lk2. And similarly, T double dash minus T naught is given as Q into ln R naught by R double dash divided by 2 pi Lk3. And since Q is common in all these three terms, we have taken Q out, isn't it? So Q is given by this overall temperature difference Ti minus T dash divided by this entire term, and this entire term is the total resistance, and these individual terms are the individual resistance for each of these cylindrical slabs, isn't it? Is it clear to everyone? Hello?
Yes, sir.
Yes,
Yes,
sir.
sir.
Yes, sir.
This is just a same extension what we have seen earlier for a flat slab, except here in this case we are looking at the cylindrical slabs. Okay. Now let's look at one more complicated, situation. As I said that uh, the uh, uh, the cylindrical geometry and the spherical geometry are specifically, are of specific interest to process engineers, primarily because if you are looking at these the heat transfer across the radial direction from the pipe, that is commonly seen situation, isn't it? So steam is flowing through a pipe, you wanted to minimize the heat dissipated outside the ambience, so you add the insulating material over the steam pipe, isn't it? So basically what you are doing, you are halting the conduction of heat from inner surface to the outside ambience, isn't it? So that is what the situation we have seen in this first case. Okay, similar situation you will see for a spherical case also, isn't it? So spherical case, if you look at the catalyst pellet, reaction is occurring inside the catalyst pellet. Because of that, the temperature inside the catalyst pellet increases and that heat is dissipated outside the catalyst pellet in a radial direction. Another situation, if you see for such cases, is nuclear reactor. In a nuclear reactor, what happens is the heat is generated inside the reactor, isn't it? And then heat is dissipated in a radial direction. Another interesting case you can see is a storage of gaseous chemicals in a spherical tank. Remember, the gases are always stored in a spherical tank. Liquid is stored in a cylindrical tank, isn't it? If you remember your design, and if you have not done the design course yet, you will get to know this later. Okay, so typically the liquid are stored in a cylindrical tank, whereas the gases are stored in a spherical tank. Okay, if you visit some industrial area, you will see wherever the storage of gases are done, these are done in a cylindrical tank. So whenever you are storing such gases in a cylindrical tank, in that case you wanted to minimize the heat dissipated outside. For instance, the example which we have seen in the starting, isn't it? So we have said that this ammonia is stored, isn't it? Correct. So in such cases, the heat transfer to the ambience or heat transfer from ambience to the system has to be minimized, and therefore you add a the resistance outside, heat resistance outside such tanks, isn't it? So in such cases, there is a heat conduction in a radial direction of the spherical tank. So this is the example of a spherical tank. Here you can see the inside temperature is Ti, outside temperature is T naught, and we wanted to see how the heat conduction through such system is going to take place. Is it clear? At least the system is clear to everyone.
Yes, sir.
Now in this case also we have to make a shell balance. As I said that why we need to make a shell balance in this case, because my radial area is going to change as I move along the radial direction, isn't it? So inside here my radial area is going to be 2 pi r square, sorry 4 pi r square, isn't it? But if I'm 4 pi ri square, and if I look at the outside surface area, that will be 4 pi r naught square. So this radial area is going to change. So in this case, again, the capital Q is going to be same because we are looking at the steady state situation. So steady state situation means capital Q here at the surface is same as the capital Q dissipated outside here. Okay. So let's make a shell balance. Let's assume a shell as shown here at the radius R, and the thickness of the shell is again delta R. So rate of heat input to the shell at the radial position R will be given by 4 pi r square into the flux at this location, so which is going to be QR, and this entire thing is calculated at R. Similarly, the rate of heat output from this shell at the radial position R plus delta R is going to be 4 pi r square QR at R plus delta R. There is no accumulation at steady state, and there is no generation also. So because of that, rate of heat input will be same as rate of heat output, isn't it? So if you do that, what we get is 4 pi r square QR at R plus delta R is same as 4 pi r square QR at R. We can take this 4 pi square QR at R on the left hand side and subtract from this 4 pi square QR at R plus delta R. What we get is 4 pi square QR at R plus delta R minus 4 pi square QR at R. And since right hand side is going to be 0, we can still divide this equation by delta R. Isn't it? Since delta R here is tends to 0, this equation is for limit delta R tends to 0, this equation represents a differential equation, isn't it? So we can write this as d by dr 4 pi square QR equals to 0, isn't it? We can take this 4 pi outside because that's a constant term. So what we can write down here is d by dr R square QR is equals to 0. Is it clear to everyone what we have done so far? Hello?
Yes, sir.
Is it clear?
Yes,
Yes, sir.
sir.
Even context is clear why we are looking at, why we are studying these systems. The context is clear.
Yes, sir. Okay, sir.
Okay, all right. So this differential equation, then we can integrate with respect to R. So if we integrate this equation with respect to R, what we get is R square QR is going to be a constant term, let's say C1. Okay. And this QR is what? QR is nothing but the heat flux. So this heat flux we can write in terms of Fourier's law of heat conduction along a radial direction. So QR is given as minus K dt by dr. We can put it here in this equation. So what we get is R square minus K dt by dr equals to C1. Again, we are assuming that this K is constant here. K is constant. We are assuming thermal conductivity is constant. Okay. But in some cases, you might not have this thermal conductivity K constant. It could be a varying, isn't it, along with the temperature. All right. So for this simple case, let's assume that this K is constant. So we get R square minus K dt by dr equals to C1. We can rearrange this equation. So after rearranging, what we get is dt by dr is given as minus C1. So minus C1 divided by this R square will be there, isn't it? And this minus 1, this K will be taken as 1 by K. So what we get is dt by dr is given as minus C1 by K 1 by R square. This is just a rearranging of this equation. Okay. Further, we can integrate this equation with respect to radius. What we get is temperature T is given as C1 by Kr plus C2. So this equation gives how my temperature is going to be distributed across the radial direction of the sphere. Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
Okay, so now in this equation there are two constants, two integration constants are there, C1 and C2. This integration constant C1 and C2 again we have to find out using the boundary conditions. So what are the boundary conditions here? At radius r equals to Ri, my temperature will be Ti, and at radius r equals to R0, my temperature will be T0. Isn't it? These are the two boundary conditions. So these are the two boundary conditions we can apply here. So from first boundary condition in this equation 2, what we get is Ti equals to C1 divided by Kri plus C2, and similarly T0 will be given as C1 by Kr0 plus C2. Again we can subtract this equation from this first equation. This C2 will be eliminated and we will get directly C1. So C1 is obtained as K Ti minus T0 in the bracket Ri R0 divided by R0 minus Ri, isn't it? And again, if you put this C1 in this first equation here, then we can find out C2, and C2 comes out to be Ti minus T0 R0 divided by R0 minus Ri. Okay. We can put this C1 and C2 again in this original equation 2, and we will get how my temperature is distributed across the radial direction of the sphere. So that is given as T is given as Ti minus T0 R0 divided by R0 minus Ri in the bracket 1 minus Ri by R. So this equation gives me how my temperature is going to vary across the radial direction R. Okay. Correct. Similarly, we can find out the heat flow, rate of heat flow Q. So rate of heat flow is given as area into heat flux at any radius r. So we can again go back in this equation. Remember, this r square QR is C1. And we are interested in finding out what? 4 pi r square QR, because that is what is going to be the area into QR. Area into QR at any radius will be same as Q, because Q is not changing along the radius. Q is same, capital Q is same along the radial direction. Small q is changing, isn't it? Capital Q is same across the radial direction. Small q is changing. So I can find out capital Q as QR at any radius into area at that radius, isn't it? So 4 pi r square QR is going to give me capital Q, but r square QR is just C1. So that means capital Q will be what? 4 pi C1, isn't it? Is it clear to everyone? Capital Q will be 4 pi C1.
Yes, sir.
Does it make sense to everyone?
Yes, sir.
Yes, sir.
Yes, sir.
So that is what we have written. Q is nothing but 4 pi r square QR, that is constant. So 4 pi C1 is going to be the capital Q. So C1 we have already found out here, C1. This C1 if we multiply by 4 pi, we get capital Q. So capital Q is given as 4 pi Ri R0 K Ti minus T0 divided by R0 minus Ri. Now in this equation, this 4 pi Ri R0, if we represent this Ri R0 as let's say Rg square, where Rg is nothing but the geometric mean radius, isn't it? Or Rm square, isn't it? So that means what? This equation is also similar to the equation what we have seen for a slab, isn't it? Flat slab. Except that the radius here calculated as a geometric mean. Okay, so the concept here is the same equation of the slab can also be applied for a cylindrical case by replacing the radius by a geometric radius. Does it make sense to everyone? Hello?
Yes, sir.
Please explain this again.
Please repeat what you are saying.
Sir, could you please repeat this part?
Okay. So here, see, here 4 pi Ri R naught is there. So Ri R naught, if I represent this as a Rm square, so what will be Rm? Rm is going to be the geometric mean radius, isn't it? Because under root of Ri R naught is what we are looking at Rm. And this Rm will be what? Nothing but the geometric mean. So what we are saying is, and if you compare, if we represent this 4 pi Rm square as a area, so then what this equation is going to be? Area into K into delta T divided by thickness. R0 minus Ri is the thickness, isn't it? So that means what?
Got it, sir. Got it, sir.
This equation is same as the equation of the slab, except that this radius is calculated as a geometric mean.
Yes, sir.
Okay, now this idea again can be extended for a composite sphere. So I have directly written that equation instead of deriving that. Anyway, we have derived for a flat slab and the composite cylindrical wall also, isn't it? So this capital Q for multiple the layers in the spherical geometry, if we are having, in that case this capital Q is given as Ti minus T naught divided by R dash minus Ri 4 pi Ri R dash K1 plus R double dash minus R dash divided by 4 pi R dash R double dash K2 plus R naught minus R double dash divided by 4 pi R double dash R naught K3. Okay, so this is just the extension of this original equation to the composite sphere. Is it clear to everyone? Is it clear to everyone? Hello?
Yes, sir.
Yes, sir.
All right. So how we have started our heat transfer course? We have just started with the appreciation that the heat transfer is used in several practically important situations. Then we started with a very simple case of conduction, steady state conduction through a flat slab. Then we have added a complexity of variable area. That is why we have looked at the cylindrical geometry and the spherical geometry, isn't it? Let's make our situation further complicated. Okay, so far we were looking at steady state situation without any heat generation, But what will happen, let's say, if there is a heat generation is also there in the system, and this type of systems are there. These type of systems are practically present. For instance, if you are having a nuclear fuel element irradiated by a high energy neutron to trigger a nuclear fission, in that case you can see that the heat is generated. If you are passing a electrical current through a wire, there is a heat generation takes place, isn't it? If there is a catalyst pellet is there, so because of reaction, heat generation takes place in the catalyst pellet. So in all such situation, you will see that there is a heat generation taking place inside the solid. So that's why we are writing there are situations in which heat generation occurs in a conducting medium, and these are the examples. Okay. Also, in some cases, thermal conductivity may depends on the temperature. In general, we take the thermal conductivity constant throughout because it simplifies our analysis. But often the cases arise where you will see that the thermal conductivity is also varying with temperature. Okay. So let's look at one such example of a flat geometry, but there is a heat generation is occurring. So there is this flat solid surface is there of thickness L and the cross sectional area of A with internal heat generation is taking place. Okay. And the temperature T1 is there on the left hand side, temperature T2 is there on the right hand side. The heat conduction is occurring in a X direction. Okay, clear? Now, unlike the flat slab example which we have started with, there we have not used any shell balance. Remember, if I go back, Yes, we have not used any shell balance. We have just directly applied the Fourier's law of heat conduction and we have obtained, isn't it? The final equations, correct? Yes or no?
Yes, sir.
Yes, sir.
But now consider a same situation, of a flat slab, but there is a heat generation occurring. Why we have not used any shell balance here? Because we were looking at the steady state, we were looking at the constant area, isn't it? That's why no shell balance was required. But when there is a heat generation taking place in such cases, or when there is a change in the area occurring in a conducting medium, in all such cases, or if we are looking at the unsteady state, in all such cases we have to make a shell balance. Okay. Does it make sense to everyone? Hello? Does it make sense what I'm trying to say?
Yes, sir.
So therefore, even though we are looking at a flat slab here, but still we have to make a shell balance. We have to make a shell balance because there is a heat generation taking place. So let us assume a shell of a thickness delta x at the location of x from the left hand side end, isn't it? Let's assume a shell here. Okay. Now, what will be the heat input to this shell? Will be the heat input to the shell?
The flux into the area.
So the rate of heat input to this element shell at x will be given as area into qx. Flux is qx here because q is now varying along the x direction. That's why it is represented as a qx at x. Similarly, the rate of heat output from this element at x plus delta x will be what? AQX at x plus delta x, isn't it? Now, in addition to this heat input and heat output, there is also one more term, and that another term is rate of heat generation in the element. The rate of heat generation in the element is given as volume into volumetric rate of heat generation. So volume will be what? Area, cross-sectional area is A, into the thickness of this shell is delta x. So that gives me the volume of this shell multiplied by volumetric rate of heat generation psi x. Psi x is nothing but the volumetric rate of heat generation. In this case, I am showing psi x as a function of x, but very often we consider this psi x as a independent of direction and just a constant term psi. Is it clear? So we in general take this psi independent of direction. So we will represent only psi. Okay. So volume multiplied by this psi x gives me the rate of heat generation in the element, because psi x is nothing but the volumetric rate of heat generation. Okay, so what will be my balance equation? Input plus generation is going to give me the output, isn't it? Unlike the previous cases where capital Q were same, here the capital Q is not same now, isn't it? Here the capital Q is not same. It is varying. It is varying, isn't it? So at any location x, my input plus generation is going to be the output, isn't it? So that is what we are writing. Rate of heat input plus generation will be output. So what is rate of heat input? AQX at x plus generation term is going to be a psi x here. And that will be the output. So AQX at x plus delta x. I can rearrange this term. And after rearranging, what we get is QX at x plus delta x minus QX at x divided by delta x plus psi x equals to 0, isn't it? Does it make sense what we have written here to everyone? Is it clear to everyone?
Yes, sir.
So we have just rearranged this equation. Only one additional term is there, that is A into delta x psi x. A into delta x is the volume of the shell, and psi x is the volumetric rate of heat generation. So volumetric rate of heat generation multiplied by volume gives me the rate of heat generation in the element, and that we are adding in the input, and input plus generation will be output. So this is what the equation we are getting. In this equation, we can take this AQX at x plus delta x on the left hand side, and rearrange this equation. What we will get is QX x plus delta x minus QX, and this delta x we divide here. So what we get is QX at x plus delta x minus QX at x divided by delta x plus psi x will be equals to 0. And we can write down this equation in a differential form because this delta x is a thickness of the shell, thickness of the element, and that is tends to 0. And therefore we can write this equation as minus dqx by dx plus psi x equals to 0. Isn't it? Now here this qx will be given by what? This qx will be given by Fourier law of heat conduction, isn't it? So this qx is given as minus k dt by dx. Again, we are assuming that this k is constant here, but for a time being we have kept it variable, but for a simplified case only we are going to generate the results. So if we put minus kt dt by dx here, what we get is minus d by dx minus kt dt by dx plus psi x equals to 0. So this is a generalized equation. Equation 2 is a generalized equation where we are not only showing this k as a function of temperature, but also the psi as a function of x. Is it clear to everyone? This equation 2?
Yes,
Hello?
sir.
Yes, sir.
Now let us make our life little bit simplified, because if we put this k also function of temperature or this psi also function of x, then this equation, solving this equation analytically is going to be difficult. Okay, so let us simplify our analysis by assuming that this k is constant and psi x remain constant as psi v. Okay, volumetric rate of heat generation just as a psi v. And let's apply the boundary condition at x equals to 0, t is t1, and at x equals to L, the t is t2. That is what the boundary condition is here. At x equals to at x equals to 0, I am going to have t1, and x equals to L, I am going to have temperature t2. Is it clear to everyone? Is it clear? This
Yes,
simplification. So this is a generalized equation. Equation number 2 is a generalized equation. We are solving it for some simplifications. What are the simplifications? We are assuming this thermal conductivity constant, and also we are assuming that the psi x remains constant, and that is psi b. It is not varying along the x direction. It's not varying along the x direction. Okay. All right. So with this simplification, this equation number 2 can be further simplified as d square t by dx square, and that is given as psi b by k. If we integrate this equation twice, what we get is t is given as minus psi b by 2k x square plus c1x plus c2. Here c1 and c2 are the integration constants. Okay, now let's apply the boundary conditions here. So if you apply the boundary condition, the first boundary condition is at x equals to 0, t is t1. If I put t equals to t1 in this case, what we get is we directly get this second constant c2, and that c2 is given as t1. This c2 we can put it here, and then we can rearrange this equation at boundary condition 2. So boundary condition is x equals to L at t equals to t2. What we get is t2 is obtained as minus psi b by 2k L square plus c1L plus c2. And if we rearrange this entire equation, what we get is c2 is c1 is obtained as t2 minus t1 divided by L plus psi b divided by 2kL. This is what we are going to get it. And this C1, C2, we can put it in the original equation, this original distribution equation. We get the temperature distribution as T is given as T1 plus T2 minus T1 x by L plus psi v x by 2k in the bracket L minus x. This is what the temperature distribution equation I'm going to get as equation number 4. Now this temperature distribution is very important here because this is not going to be linear. What I mean by this is, if I go back in this original slab, this is the original slab. Here you can see the temperature is decreasing linearly. Can you see? The temperature is decreasing linearly here. But when we are having the generation term in the slab, I will not get a linear temperature decrease like this. I will have some curved line. Curved line. In fact, see, a very simplified case. Let's say if this T1 and this T2 both are same, then also there will be heat transfer taking place. Because of the generation term, I will have some, curve like this. Okay, some parabolic, convex curve like this I'm going to get. Do you all agree with me?
Yes, sir.
Yes, sir.
So that is why we said in the conduction, not only the temperature difference is required, but also temperature gradient is also required. So here, if T1 and T2 both are same, in that case, temperature difference is 0 between these 2 points. But between these 2 points, there will be a temperature gradient because of generation term. Do you all agree?
Yes, sir.
Yes, sir.
Okay. So these are the small details are there, very often people ask in the interviews. Okay, so just keep it in mind. Okay. So this is what the temperature distribution which we have obtained, which is not linear, it's parabolic. Okay, it's not linear. It's not linear. Okay. Again, we can find out the heat flux. Now, finding the heat flux is not going to be easy in this case. Why? Because unlike the previous case, Q was constant, and because of that we were applying the applying the equation directly and finding out the capital Q, isn't it? But in this case we will not be able to find out capital Q is varying. Capital Q is varying across the length. Capital Q here will be different. Capital Q here will be different. Isn't it? It's not going to be same. It is not going to be same. So therefore, instead of finding capital Q, let us find out the QX. Let us find out the QX. So this QX will vary across the length as you progresses from 0 to L. Do you all agree? Hello?
Yes, sir.
So this equation, again, if you are looking at the book, this equation is some mistake is there in the book. Okay, so but this derivation which I am giving you here is correct. So dqx by dx, this is what the equation which we have obtained. Dqx by dx psi x equals to 0. This is what the equation we have obtained. Let's integrate this equation. So if we integrate this equation, we get qx is psi vx plus c naught. Now this c naught and this c1, these are related because these are all already these are derived from the same equation, isn't it? These are related. If you look at their relation, you will get that C naught is just as minus KC1. That's it, isn't it? Because this minus sign we have negated here and integrated. This K is taken out, so that becomes d square T by dx square, isn't it? But instead of looking at this differential equation, if you start with the another differential equation, this differential equation, let's say the integration constant is C naught, but that integration constant will also be related to this C1. Do you all agree? Hello?
So can you please explain again?
So see, remember how this equation is obtained? This equation is obtained from this original equation. Isn't
Yes,
it?
sir. Yes, sir.
But this equation, this original equation is given in terms of Q, whereas this second equation is given in terms of T.
T.
Isn't it? So this equation we have obtained in terms of T because we have added this Fourier's law of heat conduction by using this additional term kT dt by dx.
Yes, sir.
Isn't it? So this minus sign got eliminated and this K we have taken it on the left hand side, isn't it? Correct.
Yes, sir. Yes, sir.
And then we have obtained this integration constant C1. Correct?
Yes,
So
sir.
this integration constant is nothing but what? This integration constant also had this effect of k, because we have already divided this entire equation by k, and psi v by k we have put it here on the right hand side, and then we have added the integration constant c1. Correct?
Yes, sir.
So that means this c1 and this c0 is related. But this c0 will be nothing but minus kc1. You get it?
Yes, sir. Yes, sir.
Yes, sir.
Okay. But this c1 we have already obtained. So we just put it c1 here. We can find out c0. So we get qx is this equation. Okay. One more, I think correction. Maybe I'll just do it here itself. Another correction here is just a minute. Another correction is needed in this figure that I will do it immediately. Just a minute. It should be this cell, isn't it? Now it is correct. Is there any question?
The screen sharing.
My screen is not shared.
Yes, sir. Your
Yes,
screen
the
is
screen
not
is not
shared.
shared.
What is the question? Still not able to get what is
The
the question?
screen is not shared. Screen.
Acha, screen is not shared. I'm just doing it. Just a minute. I'm doing it. Sorry. So my screen is lost just now or earlier also?
No, sir. We were
So
able to
when
see
you
it. Just
started
what you were corrected.
making changes in the diagram, we couldn't
Okay,
see
so when I
the
started
screen after
making the
that.
changes in the diagram, then it is lost.
Yeah.
Okay, thank you. Okay. So this is this figure also I have changed. Can you see now?
Yes,
This
sir.
figure also I have.
Yes, sir.
Yes, sir.
Okay, so these are the small mistakes are there in the book. So I have just eliminated this here. Okay. All right. So what is the time now? Okay. Okay, so the final equation which we have obtained here is this. Qx is given as psi Vx minus k in the bracket T2 minus T1 by L plus psi V by 2k L. Now here this Qx, if you wanted to find out capital Q you can find out at any location X by multiplying the corresponding area, isn't it? Corresponding area and keeping the value of X there. Is it clear? Is it clear to everyone?
Yes, sir.
Yes, sir.
So that means the Q at this surface, capital Q at this surface and capital Q at this surface is not going to be same. It is not going to be same, unlike the previous cases which we have seen. Okay. Is there any question so far? Or everybody able to get it? Is
Sir,
it
I'm
clear?
not able to understand. C0 is equals to minus KC1.
Okay. Okay. So see this equation number 2, can you see?
Yes, sir.
If you integrate this equation number 2 without simplifying this inside, what you are going to get? Minus psi v. This minus psi v is going to become plus psi v, isn't it? Plus psi v x plus c0, isn't it? If you integrate
Yes,
only once. If
yes,
you
sir.
compare that with this equation, so c0 and c1, what will be the difference? See, this is integrated twice. What will be the integration first time? If you integrate it first time, what you are going to get is dt by dx will be given as minus psi v k x plus c1, isn't it? That's what you are going to get in the first integration.
Yes, sir.
If you compare that with the original integration here, without simplifying that, what you are going to get?
Psi x by k.
So that's what I'm saying, that divided by k term will not be there here. So that is why this C1 will be what? The C0 will be what? Minus KC1 if you rearrange things.
Got it.
You got it? It's not same because here this integration we are doing in terms of t, but in the original equation here integration we are doing in terms of q, and t and q the difference is going to be by minus and this k term, because that is what you are dividing in the simplifying case. This minus sign and this k you are dividing. Does it make sense now?
Yes, sir.
So that's why this C0 will be minus KC1. I have directly used it, but you can derive it also. I am giving you how it can be obtained, but you can derive this easily. It's not difficult. Make sense?
Yes, sir.
Or see, you can derive from this equation itself. See, if you integrate this equation first, only once, what you are going to get? dt by dx is equals to minus psi v k x plus c1, isn't it? Correct. And what will be q? Q will be minus kt dt by dx. So if you multiply minus k here in this equation, then what you are going to get? Minus psi v k. That k get cancelled out. So psi v x minus psi v x. So that minus psi v x is going to become plus psi v x plus this minus k you are multiplying here. So minus k c1 x, isn't it? And if you compare that with the original equation, this equation, C0 will be just minus KC1. Clear or not clear? Still not clear?
Clear, sir. Got it.
All right. So I am saying you integrate this first time and then represent this equation in terms of Q and compare with the original equation this after integration, you will directly get C0. C0 is going to be minus KC. That's what you're going to get. All right. So I think it is 10:47. So we will just introduce the next system and we will not derive anything for this system. But we will discuss and then we will conclude today's class. So now again we are adding one more difficulty in our analysis. What is the difficulty? In this case, in addition to the generation, in addition to the heat generation, we are also assuming a cylindrical system. So cylindrical system means your area is also varying. Remember, in the previous case, my area was constant, isn't it? Now in this case, the area is also varying. And also, in addition to that, we are assuming that there are two layers are there. First one is the metal layer in between here, and outside there is a insulation layer. So in the metal layer, there is the heat generation taking place because of the electrical dissipation. Okay. Whereas in the insulation, there is no heat generation. So there are two layers. So here what we are considering is there is a electrical wire carrying the current, isn't it? The wire of radius Ri has a layer of electrical insulation over it, R0. So up to Ri there is a metal wire is there, and outside that there is a insulation is there. So outside temperature is T0. The thermal conductivity of the material of the wire is, the metal wire is Km, whereas the thermal conductivity of the insulation is Kc. And the volumetric rate of heat generation is taking place only in wire, only in a metal wire. So heat generation is taking place only in this metal wire. There is no heat generation taking place in this insulation layer. Can you see? Are you all able to understand at least the system? What I'm trying to say?
Yes, sir.
So what I'm trying to say here is there is a electrical wire conducting a current, and because of current because of the resistance of the electrical resistance of the wire, some of the current will dissipated to a energy, isn't it? So heat will be generated inside the wire, isn't it? And that again, outside of this electrical wire, we always have the insulation just to protect from the electroculation, isn't it? So that protection layer will act as a insulation to the heat dissipation outside. Okay, that is what the system is. Now we have to derive the equation for this entire system. So complications here with respect to the previous case is here not only the heat generation is there inside the conducting medium, but also the area is varying in the direction of the conduction. Also we are assuming two layers. One layer there is a heat generation is taking place, and another layer there is no heat generation taking place. So these are the three complications we have added in the system. So we will derive the equation of this system again in detail in the next class. Okay, so let us stop here and we will discuss if there is any question so far. Is there any question so far? So almost I think. Okay, so please ask your friends to attend the classes. I am giving you this recording material. And I definitely wanted, this is a request. This is a request. I understand that the situation outside is not good. But if you attend the class, that will not only motivate me, but also, you know, it keeps things in a track. If you know, students are not attending, then in this online semester, I'm only get to know the screens and nobody is there. You know, it completely demotivate the instructor. So please help me by attending the classes. Okay, if you attend, more student attend, then you know that interest is there. Okay, all right. So let us stop here unless.
Excuse me, sir.
Please go ahead.
Sir, when will the tutorials be held for this class?
I'm sorry. So can we have a tutorial maybe today or tomorrow? I wanted to have one common tutorial for all the batches. So have you discussed among yourself? Hello.
Sir, maybe Monday.
Monday at what time? At what time you wanted to have?
So maybe 3 to 4.
So I'm okay if it is you know, okay for all of you. Monday 3 to 4 we will have a tutorial common to all. If everyone is.
So what if we like have a poll and after that we can like
Yes.
send it to you through mail? So it will be much better. Because if in this meet all the people will start speaking what they prefer, so I don't think we will be able to decide what exactly. So
No,
I think
so we have already lost 1 week. So when you will be, you know, able to convey this to me?
sir, I will have a poll today itself and I'll mail it to you, whatever the result will be today itself.
Okay, so will it be on Monday or some other day? Some other day, that then it's okay, because then we also have a chance to make that up, isn't it?
Yeah.
Otherwise, if it is Monday, then it can happen only in the next week, isn't it?
Yeah, I get it what you are trying to say. So, or we can like have a poll right now and I'll like let you know in an hour or so.
Okay.
If everybody agrees with it.
Please go ahead.
So we may do that. Like you can schedule a tute for today, and from next week we will conduct a poll and let you know.
Okay, so that's perfectly all right. So let's have a tutorial today from 3 to 4. That's what you are saying?
Yes, sir. Okay, sir. That's like
3 to 4 you are saying, or 2 to 3 you are saying? Which time is better?
So 2 to 3 we already have a tutorial. So 3 to 4.
Okay, so 3 to 4 we will have 3 to 4 a common tutorial for all the batches. Okay, all right.
Okay, sir.
If there is any change in the schedule or something, then you find out, and next week onward we will stick to the another schedule. Okay.
Okay, sir.
Oh, okay, all right. So let's meet around.
Sir, today 3 to 4 we might be having one more meet. So can it be some other time?
Is
Which
it BBL 751 because that is from 11 to 12?
But today it will be from 3 to 4
No,
only.
no, they changed the class. They changed the class timings. It is 11 to 12 only.
Okay, so
Okay.
then it is settled. Thank you. Okay,
Okay.
3 to 4 we will have a tutorial. All right.
Okay, sir.
Thank you so much for attending. All right.
Thank you, sir.
Thank you, sir.
Thank you, sir.